Hey guys, how's everyone doing? I'm gonna wait a bit and we'll get started. Today is on spectroscopy and on sort of interpretation and how you'd approach one of those combined questions where you're given an MR, some information, a spectra, and everything, and how would you approach a question like that? So we'll go through step by step on how to approach. I'm just going to wait a couple more minutes, see if anyone else is trying to join up. We've got a bit of a sparse crowd today, so I'm kind of hoping other people will join. Otherwise, we'll need to have a think about this. We should get started in like 2 minutes. Again, just waiting to see if you know other people in the group chat or anything like that and you want them to get them to join, please send them a message just so we can get more people in. Right, let's get going. So the first thing we're going to talk about is identification by test tube reaction. So this is anything that is to do with, so these aren't like your infrared or your mass spec, but these are the simple kind of things that you're probably going to be doing in your lab, and you're probably used to doing most of these practicals before. Hopefully you guys can all see my screen. Let me know if you can't. So you need to know the test for alcohol, aldehyde, alkene, and carboxylic acid. So these main three you probably all should be quite familiar with. Alcohol maybe haven't got previous with. So identifying alkanes versus alkenes. Well, this one is the very famous bromine water. So if you're adding if you've got an unsaturated compound with a double bond, then there is the orange solution when you add bromine water turns colorless. And if there's no double bond, the solution will stay orange. Explanation of this reaction is basically you have an electrophilic addition reaction. So does everyone know what an electrophilic addition reaction is? Basically what's happening is you get I'm just going to quickly draw a quick description of this. And then you just get H, C, H. Sorry, I'm trying to do this with a mouse. It's a bit more challenging. Yeah, minus. And so then these electrons go over to the H. And you end up with the final product. And you just end up having dibromoalkene. That makes sense? Sorry, can I ask someone to mute? This is yeah. So bromine water and alkenes. So the bromine atoms add across the double bond, electrophilic addition. That orange solution then turns colorless. Yeah. So bromine water and alkenes. So the bromine atoms add across the double bond in an electrophilic addition reaction. That orange solution turns colorless. Identifying halogenoalkens. So these are your bromos, your iodos, your fluoro compounds. You do that by adding acidified silver nitrate with dilute ammonia and a concentrated ammonia, and you're expecting a precipitate to form. This is exactly how you would identify any halogen compound in any other kind of chemistry lab setting. So it's the same process that you've probably done time and time again. Acidified silver nitrate, or you just add silver nitrate with nitric acid as well as ammonia, dilute and concentrated ammonia to tell the difference between some of these that might appear quite similar. I mean, obviously, it's basically the main difference between white and cream. Okay, now identifying again, this is basically due to nucleophilic substitution between hydroxide ions from sodium hydroxide and the halogenoalkane. The bond between the carbon and the halide is broken, releasing the halide ions. Identifying alcohols, you have to warm with acidified potassium dichromate, and you're expecting an orange solution to turn green with primary and secondary alcohols. it doesn't work with tertiary alcohols, and it's because the primary alcohols are oxidized to aldehydes, the secondary alcohols are oxidized to ketones, and the tertiary alcohols are not oxidized at all. Okay. Aldehydes, you have two potential tests. Tollens reagent, which is basically you warm the aldehyde with tollens, and you're expecting a silver mirror formed on the inside of the test tube. And this is because Tollens reagent is an alkaline solution containing silver ions, which are dissolved in a dilute ammonia. The silver ions become reduced by the aldehyde, which is oxidized to form a carboxylic acid. The other reaction is Fehling's reagent, where you basically warm aldehyde with Fehling's solution, which is a blue solution, and we would expect it to form a brick red precipitate. Fehling's solution is an alkaline solution of copper-2 ions dissolved in ammonia. For all the biologists in the room, is Fehling similar to another reagent that you might have used before? Anyone? Yeah, it's very, very similar to Benedict's solution. Because it's the same color changes, and it's virtually the same because they're both solutions of copper-2 ions dissolved in ammonia. Yeah. Okay, so acidified dichromate is another reaction. So with an aldehyde, it is oxidized to a carboxylic acid, and it becomes orange to green. So it's the same as the other one. Benedict, what's the difference? Well, Fehling's it's what it's dissolved in, basically, but there are no significant differences in the ions and the color changes. It's just what it's dissolved in. Identifying ketones, basically, you're just expecting that no reaction will occur with any of these, because with a ketone, it can't be reduced any further. Identifying carboxylic acids, you add a carbonate and bubble the gas through lime water, and you're expecting effervescence and bubbling because you basically form carbon dioxide. And once you form that carbon dioxide, it's released. Also, once you test with acidified dichromate, tollens, and Fehlings, you're also expecting no reaction to occur. Carboxylic acids cannot be oxidized any further. They're the end of that reaction pathway. So those are basically your lab tests. Now talking about mass spec. So I'm not really going to go into a lot of detail about how mass spec works, but this is to do with the time of flight mass spectrometer. You vaporize the gas, you pass it through the spectrometer, you ionize the sample. I'm not going to go into a lot of detail on this. Once you've ionized the sample, you basically accelerate the positively charged ions through an electric field. So, and this is to do with the electric field is basically the negatively charged attraction plate. Then the more positive the charge, the more it gets attracted through. And then after acceleration, all ions will have the same kinetic energy. And therefore, then they drift too much, and they're detected by the reader, and it then generates a mass spectrum. Now, remember what you need to know. The molecular ion peak is the peak furthest to the right. That's the heaviest peak, and so the last peak, and it will give you the MR of the compound that you're looking for. So whenever you're approaching a question like this, the main things to look for in a mass spec are MR right at the end and the molecular ion peak. The height of the peak is related to the abundance of that isotope. So this is similar to something you'll do next year, which is NMR, which is nuclear magnetic resonance. And you do have some peaks where the height correlates to the relative quantities or abundance of that isotope. High resolution mass specs go further, low resolution mass specs less far. So let's take a moment just to think about what you're expecting to see in this. So if you guys want to type it in the chat, anyone who's watching outside on the YouTube, or if you want to just take a moment to pause and think about this, then we'll go through the answer. Anyone want to have a go of what peaks they'd expect to see? Just put through the chat. Anyone? Cool. If there's no one to say anything, we'll go through the answers anyway. So we would basically expect peaks because remember, chlorine exists as Cl2. We would expect therefore peaks at 70, where there's two 35s, 72, where there's a 35 and a 37, and 74, where there's two 37s. And because the ratio is 3:1, we expect that a 35 and a 35 is going to be 9 of them. A 37 and a 35 is going to be 3 times 1 times 2, which is 6 of them. And then a 37 is going to be 1, so 9 to 6 to 1 ratio. So therefore, we're expecting it in a 9 to 6 to 1 ratio. Does everyone make sense with that? The last thing we're going to do before we go through a couple of practice questions on this is IR spec. So this is probably the one that you might be the most concerned about or the most worried about. But basically, all this is to do with is infrared waves. So infrared waves are part of the infrared waves are part of the electromagnetic spectrum. Electromagnetic spectrum basically is just waves of energy being passed through. And so when infrared radiation is passed through a compound, some of that radiation is absorbed by the bonds within the molecule, and some is transmitted. Infrared radiation measures the wavelength, where wavelength equals 1 over wave number. You don't need to worry about that too much. But basically, what you need to know is when the IR is passed through the compound, each of the bonds absorb a different amount. And that different amount is unique to the bond itself. And that creates the wave number kind of, that creates the wave number structure to it. Fingerprint region between 500 and 1500 is unique for all molecules. It represents the wave numbers absorbed by the carbon-carbon single bonds and the carbon-oxygen bonds, as well as the vibrations of the whole molecule. And this is how we identify structures, because we can identify structures relative to the samples in the database. Your basic job is to measure, look for the IR spectrum, look for these key regions when you're approaching these, look for these key regions of density, look at where they're located, and compare it to the data sheet. Now, remember, you're going to probably make a sense check on this. If someone tells you that this is a molecule that is going to react with Tollens reagent, you're probably not going to identify this as an amine, right? You're probably going to think, okay, there's something else going on here. Or if for this molecule particularly, it's probably going to be a molecule with a carbon, oxygen, and an OH. Well, that to me indicates carboxylic acid quite significantly. And therefore, if they tell you that if you're looking at it and you're like, oh no, this looks like a nitrile, it's probably not going to be that then. If you know what I mean. So do perform a sense check very fast. What bond does this trough represent? C double bond O. Why? As in, where is this from the data sheet? So remember, identifying that it's a trough around 3000. Is it a broad peak or is it a narrow peak? Broad peak. So is it going to be Sia? I wonder. Yeah, it's probably going to be a carboxylic acid peak. Yeah. So the trough is probably going to be the OH bond in carboxylic acid because it's a broad peak between 2500 and 3000. So can we identify some of the functional groups present? CHOH, C double bond O. Yep. So OH, C double bond O, and then obviously going to be CH. But because the OH and C double bond O are separate, we know it can't be a carboxylic acid. I won't do this one. There is a bit of a link between infrared radiation and the greenhouse effect, because the Earth absorbs some of the energy from these waves and emits them back to the atmosphere as longer wavelength infrared waves. Greenhouse gases include carbon dioxide, water vapor, and methane. These greenhouse gases absorb IR radiation and heat up, which increases the kinetic energy. The rapid increase in carbon dioxide levels over the last 100 years is due to the increased combustion of fuel. This has then led to the largest increase in temperature the planet has ever known in the shortest period of time. Cool. Does that all make sense? Let's put that into practice for a little bit. This one. This one. That's A-level biology. Sorry, let me just find a good question. Don't we need to know all these things? All that's uses, e.g. alcohol, the test for alcohol in breath. It depends on your spec. I think some specs do need to know it. Some other specs don't. It really does depend on what spec you're doing as to what you really need to know. Okay. So have a go at this. So the question is that alcohol, if you can identify alcohol E, identify what organic product F is then. Ketone, is that, so are you saying F or E is the ketone? F, why? Of yeah, so there is a narrow peak at about 1.8. So what does that indicate? C double bond error, yeah. But because there's no broad peak, there's no indication of an OH. So it can't be a carboxylic acid. How can you tell that it's not going to be a how can you tell it's not going to be an aldehyde? Yeah, it's heated under reflux. Perfect. So what does that indicate about alcohol E? It's secondary, yeah. Now, can we deduce which one it is? Secondary. So now can we deduce what alcohol E is and then what product F is? And by naming. Propan-2-ol. How did you conclude that? MR of 59. Perfect. Well done, guys. Okay, so we've worked together and we've deduced that. Let's do one more. Yeah, have a go at this one. So this is a sick 8 marker, so I want you to properly deduce these step by step. Empirical formula. Perfect. Yep, that looks about right. Cool, guys. All right. I said at the end of the session that I leave like the rest of it open to questions. So I'm gonna leave the next 10-15 minutes open to questions if you guys have any. We went through a lot today. We've got one more biology session on after this, which is on Sunday, 4 to 5, like last week was, and that's on practical stuff. It's on transects and quadrats and all of those investigative approaches. So I hope you can join us for that. Any questions for me before we leave up? Notes as in what? As in the slides? I can't share the slides. Usually for the biology sessions, if you guys wanted, I would be able to share notes with you because those are my own personal notes, but I can't share slides, unfortunately. Any other questions? You'll be uploaded to YouTube. That's what it generally gets done. Why is there an M+1 peak? It's because you've ionized everything. So, yeah, it's because there's you've ionized it all, so it should be M+1. Because everything is ionized, so it gains an electron. Why isn't everything else +1? Most things are +1 as well. They do move also 1 up because they're also ionized. Some of them, but yeah. So some of them are also to do with the fact that there is carbon-13 present. Any more? Otherwise, I'm just going to end the session there. Hope to see you guys on Sunday. Bye.